My name is Ruby Yi, and this is a brief summary of my research on mixing in the Arctic Ocean. Now, mixing is exactly what you think it is. Take two fluid masses with two different properties. Milk is cold and heavy, while coffee is hot and light. The differences in their properties are erased gradually on their own through molecular diffusion, but stirring with a spoon causes mixing to occur quicker. In the ocean, the two important properties are heat and salt, which determine density. You could, for instance, have warm, fresh, light water mixing with cold, salty, dense water. One important source of ocean mixing that I studied in my project is turbulence. Think of chaotic motions in the fluid, with lots of swirling whirlpools called eddies. Before, the spoon sped up mixing by making the coffee turbulent. In the ocean, winds and tides drive turbulence. But why do I care about turbulence? And why in the Arctic? Well, turbulence is a small-scale effect that influences larger systems. It influences density distributions, which affect currents, which impact global climate. In the Arctic, turbulent mixing has the potential to bring deep, warm water to the surface, leading to sea ice melt. On a 2018 research cruise in the Canada Basin, an instrument called a microrider, which measures temperature 512 times per second, was lowered down through the water at all the dots on the map. These temperature recordings give us something called the eddy diffusivity, that is, approximately how much mixing happens because of turbulence. Recall that the eddies are the swirls characteristic of turbulence. Now, the microrider gives us enough information to make something called a spectrum, which looks like this. It shows us how temperature variance per meter is related to the size of the turbulent eddies. With some processing and predicting based on theory, this data tells us how turbulent the water was. The challenge is that our temperature probe is limited by how fast it's able to see its environment. Think of how a thermometer needs time to notice that the water around it has heated up. As a result, we can only trust our measurements in a certain range. So, we use a theoretical prediction for how the curve should be shaped, and then we fit it to the data range which the sensor was able to see. For instance, these two spectra are identical. If we decide the yellow region is most reliable, we match based on what our blue data looks like in that region, and our fit looks like the red curve. But if we decide to use the highlighted region on the right, our fit looks a lot different. There aren't many turbulence measurements available at all, especially not in the Arctic. Throughout the project, I've taken a first look and gained a better understanding of the challenges associated with this type of data. Thanks for listening.